Thank you so much for having me here. I'm excited to be at MobiCom for the first time. Although I've read many papers from this conference, it's a pretty exciting work that everybody here does. I'm enthusiastic to be here to talk about work that many collaborators of mine have been doing on what we call four systems perspectives for human-centered machine learning. Needless to say, machine learning has had a tremendous amount of momentum over the last decade. From my perspective, there are three key trends that have led to this momentum. First, many decades of academic research, much of which stayed in papers because of lack of data, which has been unleashed over the last couple of decades, first through the advent of the internet with large amounts of data available from the web, later on through competitions like the Netflix Challenge and ImageNet, they really have brought the communities together. And more recently, with the advent of mobile and wearables like this one, we've seen an orders of magnitude increase of data available to machine learning. So we can train bigger and bigger models than we've ever done before. But of course, a big challenge is scaling that. And the advent of the cloud, GPUs, and more recently, machine learning specialized hardware has really allowed us to deal with larger scales of data than we've ever done in the past. And with that, we've had tremendous milestones in this field, from creating superhuman players for games like Go, through making the possibility of self-driving cars seem tangible, all the way to saving lives every day using wearable devices. So that's exciting. But despite the tremendous momentum and impact of machine learning, it's easy to forget that there's no machine learning without humans in the loop. Humans are key to everything that we do. They define the applications that use machine learning. They design the underlying systems, train the models, define the evaluations of the systems, deploy the applications, and ultimately are impacted by the decisions of these AIs. The tools that we use to develop, for humans to develop these machine learning systems look a lot like this. And we're far away from creating tools that feel more natural, maybe like this one in a different domain. But over the last decade, we've been working on a number of systems that will empower more and more people to do more with machine learning. And I believe that systems like Spark or TensorFlow, or ones that we built like XGBoost, MXNet, and CoreML, have really been catalysts for the momentum of machine learning. Without systems like this, we wouldn't be where we are today. A common theme for all the systems that we've been working on is not only that we're developing systems for machine learning, but we're using machine learning techniques to making the systems possible in the first place. We call these learning-based learning systems. And today we're going to talk about systems in four areas. In particular, how to help more developers create models, how to deploy this on a wide range of devices, how to help product managers and machine learning engineers collaborate to direct AIs, and finally, how to build trust and transparency into machine learning systems, a key challenge of this decade to come. A decade ago, when we started working on machine learning systems in general, if you wanted to create a model and deploy it, it was really hard. You basically had to start coding everything from scratch. You take a class with me, you learn what the algorithm was, and you implement it all yourself. And this created a huge barrier for adoption for machine learning. So systems to democratize machine learning have been catalysts for this huge transformation. And I'll briefly mention two systems that we were heavily involved in. First and foremost, when you're creating a machine learning application, coming up with the right kinds of features that these models use is a really challenging, laborious task. My student Tianqi Chen wanted to facilitate this process and to enable anybody to quickly build nonlinear features. And to do that, we created a system called XGBoost, which is a fast and scalable tree boosting system. It's really simple to use and can work on a wide range of data types. And unlike deep learning systems, it requires a lot less expertise and fine-tuning. And because of that, XGBoost has become the de facto tool in machine learning and data science in industry and academia. It's basically used in every major company around the world today. It's used by new data scientists. So for example, over half of the winners of Kaggle competitions use XGBoost in their solution. And it has been used for major scientific discoveries. So for example, the CERN Large Hadron Collider has reported that their physicists have used XGBoost as part of their key particle physics discoveries. So it's exciting to see systems like this having impact in the real world. And every system that we're going to talk about today is in production at scale in major companies. Now, if you look at the key drivers for adoption for XGBoost, I view those as being in two areas: scalability and usability. With techniques like sparse quantile sketches and out-of-core computation, we allow developers to deal with more data than they can fit on one machine. And this has enabled large-scale data processing using XGBoost. But that hasn't been the only driver for adoption. The second one has been the usability piece, the ability to, out of the box, deal with a wide range of data types, or an end-to-end system that's fully part of XGBoost, where we natively deal with missing data in a principled way. So because of that, we significantly decreased the burden of developers to adopt machine learning. And we wanted to take this idea and ask, can we push it further? Can we allow even more people to do more with machine learning, to be creative? And the challenge is that pretty much every system today requires you to tell it how to solve a problem, not what problem you want to solve. In a machine learning perspective, this means pick a model and tell me what that model looks like, and that's how you talk to a system. But this is really hard for folks that don't have a machine learning background. In contrast, we created a system called TuReCreate, which is now fully part of Apple's ecosystem with a system called CreateML, where instead of starting from a model, you start from the application you want to solve. I want to build an image classifier, an object detector, a recommender system, or an activity classifier. And using a combination of machine learning techniques and some rules, we automatically do feature engineering, model selection, training, and deployment for you. And because even though we usually talk about massive amounts of data, most applications start from small data sets and grow from there. We made transfer learning, the ability to learn from small data sets, a first-class citizen in every model we support or every task we support. And with a system like this and a few lines of code, a developer can build and deploy an application. So for example, our friendly developer here with no machine learning background can build an object detector like this. And with just one line of code change, he can transform his object detector into a 21st century version of the clapper. Only old folks like me will understand this joke. Haha. And with another line of code change, you'll be able to create and train your own style transfer model. So this idea of making machine learning accessible and very simple has empowered a huge number of applications that are super creative. So it's not just the major applications like Rosetta Stone that use TuReCreate, but we have folks doing things from, on the top left here, help you learn to do a better deadlift, all the way to the bottom right, solving a very fundamental task of learning to tie a tie. We have an app for that. So by making machine learning easy to build and easy to deploy, you can empower more and more people to build intelligent applications. If you've taken a class in machine learning, maybe one that I taught, Machine Learning 101, let's say, you might think that machine learning looks like this. You start from some data, you train a model, and you evaluate it. Or maybe worse. You start from some data, you train a model, I show you that my curve is better than your curve, and I write a paper about it. In reality, though, building and deploying applications that have impact in the real world requires you to do a lot more than that. Evaluation is key, but the whole life cycle of this application is very fundamental. So we'll be working on tools that empower more people to do more across the life cycle of machine learning applications. In particular, let me talk a little bit about deploying these models into devices. The challenge here is that the state-of-the-art models are getting more and more computationally intensive as well as memory intensive. So if you want higher accuracy, you have to do a lot. And this has become a bottleneck. To address these problems, we've seen a wide range of machine learning-specific hardware that has allowed us to solve bigger problems than we've ever done before. Basically, every device that we ship at Apple today now includes a neural engine that allows you to do neural networks in an accelerated way in silicon. That's exciting, but now we have a new challenge, which is how do you transform your code and execute it on new ASICs? In the context of Apple, we've created a system called CoreML. We can start with models from standard libraries like TensorFlow, MXNet, or to Recreate, drop into your developer environment Xcode, and they can easily be deployed into your application. And in the process, we optimize for it. So we decide, for example, that this part will run best on the neural engine, this part on the GPU, this part on the CPU. And this process has enabled more and more developers to build and deploy these models. In fact, we're seeing thousands and thousands and thousands of applications that use CoreML today. Pretty much every major application in the App Store uses CoreML, which is exciting. But we also see a wide range of new and creative applications. Here's one that I really love. It's called Home Court. You put your phone or iPad, and it tracks you as you're playing basketball and helps you improve your game by showing you where you did well and where you didn't and what your form was like. It's a really cool application of machine learning and AR. Now, we talked about this in the context of Apple and the neural engine, but there's a wide range of new kinds of hardware targets for machine learning, including here the Google TPUs. And this is exciting, but now not only do you have to think about what models you're going to build and what frameworks you're going to use, but you think about how to optimize every model of every framework into every hardware target. And this can be a very overwhelming process. If you're building your own silicon, this is even worse. So for example, in this Vita project from the University of Washington, just to evaluate a model on this new device, we naturally have to implement a large amount of microassembly code. So we want to make that easy. A natural way to do this is to start with a high-level data flow representation of the computation and map it to low-level kernel operators that have been optimized. A very known way of doing this in the context of GPUs is NVIDIA's cuDNN, which has a wide range of optimized kernels like the 2D convolution. The challenge, though, if you have a new type of operator or if you want to do something as simple as operator fusion, which might provide a speed up, you have to implement a new low-level kernel, which is a very intensive engineering task. And we have to do this not just for NVIDIA GPUs, but for every possible hardware target. And we have to do this for a fast-growing set of workloads in the machine learning space. This is a very overwhelming process. And it really calls for new kinds of systems to support the deployment of machine learning models across a wide range of low-power hardware targets. So here, there's a new system to be built where the system would enable machine learning to do better on devices. The challenge, though, is that this optimization usually requires a large number of highly specialized folks who work really hard. And so the question that my student Tianqi Chen and our collaborators wanted to ask and solve is whether not only can we create a system to help deploy machine learning models, but can we use machine learning to automatically optimize the system? Here's another example of a learning-based learning system. So the system is called TVM, and it builds on the Halide project from Berkeley, which separates the specification of computation from the specification of the schedule, how it gets optimized to different device backends. In our case, we have a computational graph for deep learning models, which gets translated into a TensorFlow expression language, which can then be scheduled on device. The challenge, though, is these optimizations have a large number of parameters or possibilities that have to be selected, billions of them, and it will be really hard to do this by hand. To address this problem, we create a system we call AutoTVM, where we learn to optimize highly optimized kernel implementations, hardware-specific kernel implementations of machine learning models. So I'm going to tell you a little bit about AutoTVM next. The idea here is that you start from a high-level specification of the deep learning program and the search space for hardware. AutoTVM and TVM generates code that can run on a device, and we run it on the device to evaluate the metrics that we care about, like latency, energy, memory, and so on. To give you a sense of what this looks like, we have to do lots of experiments on a lot of devices. Here is a first version of what the system looks like. Now the cables are a little straighter. And using this model, using the system, we can evaluate a particular set of choices, and we can feed it back into the optimization. The challenge, though, is that each trial can take a second or more, and just doing a testing of different configurations makes this process really slow. So instead, we wanted to build a cost model that helps us understand what the hardware specification is and how different configurations will lead to different performance metrics. The challenge, though, is how do you come up with these cost models? Doing it by hand for every hardware target is really hard. So we took a machine learning-based approach where we took a parameterized family of cost models and used the measurements from devices to train these parameters for every hardware target. Now, of course, defining this family of cost models is the crux here. And the approach that we took was not to use the high-level definitions like the loop sizes and thread choices, because this misses out on task-specific knowledge. But instead, we took the abstract syntax tree, or AST, as the features that we use for the machine learning model to predict the cost of a particular computation. We've implemented a couple of different machine learning models for this. A boosted tree model, which is simpler and easier to implement, but slightly less accurate, and a tree GRU model, which is a bit more accurate, but much slower. Today I'm going to just report the boosted tree model, which obviously is going to use XGBoost, since it was simple and effective. So we evaluated the system in three ways. We want to compare to hand-optimized, see if we can get close to human-optimized kernels. If we scale across hardware backends, and if we can deal with a wide range of workloads. Perhaps one of the most optimized low-level kernels for deep learning is NVIDIA's 2D convolution kernels on GPUs. This is one of those that are used everywhere, and the question is, can you learn to do better than that? If you use black box optimization, even with 800 trials, you're not able to quite reach the performance of cuDNN. But using a model-based approach with ASTs and AutoTVM, we're able to beat the performance of cuDNN by about 50%. And this is incredible because the system was optimized by strong engineers across a lot of work. In fact, if you look at end-to-end performance on a number of different hardware backends, NVIDIA GPUs, ARM CPUs, and RGPUs, we're seeing significant gains for taking a machine learning approach to optimizing systems. Now, these results I've shown so far are on computer vision tasks, which have been the focus of a lot of optimization already. If you look at newer tasks like LSTMs, reinforcement learnings, and GANs, we see even higher gains in terms of the performance because the systems haven't yet been optimized so much for these new kinds of workloads. These results really illustrate the fact that an automated approach is really important to keep up with the fast-moving machine learning field. Now, sorry. So far we talked about inference tasks, but training models has become exponentially harder as we're training bigger and bigger models. In fact, if you're naively trying to train a machine learning model, the AlphaGo Zero model on EC2, you'd have to pay about $1.5 million. That's more than the cost of a derelict house in the Bay Area. And that's not the only problem. The carbon footprint of training these models has become really significant. So optimizing training is also important for environmental issues. So we've been extending TVM to not just deal with the inference task, but also the training task. So here, instead of working from the high-level computational graph optimization piece, we changed that for differentiable high-level intermediate representation, which automatically generates gradient programs for training, and they can be optimized with AutoTVM in the same framework. Stepping back, TVM has already had a tremendous amount of impact in the industry. AWS created a new deep learning compiler service called SageMaker Neo using TVM. And Facebook and Microsoft have reported the impact of TVM in production for both cloud and mobile workloads. TVM is now incubated in the Apache Foundation, and it has a huge number of contributors. So TVM is an example of a system for machine learning which also uses machine learning to optimize itself. And the question that we wanted to ask is how far can we take this concept of learning-based learning systems? In fact, one of the hardest tasks in machine learning is to define the problem you want to solve and collaborate around it. So can we use machine learning to help learn to solve the task you want? Here's a small step in this direction. In particular, we want to help product managers direct the behavior of AIs. Let me give you a more concrete example of that. Netflix has talked a lot about the fundamental gap between the work that machine learning engineers do and the products they're trying to build. So for example, when they've created the Netflix challenge, how long is that? Over a decade ago, the idea here was to get people to predict what rating somebody would give to a movie they haven't watched yet. Seemed like a great task. They minimized some squared error. It was easy for machine learning training, but they reported it was hard to make this useful in production because it was a huge gap between this problem and the real business problem they were trying to solve, which perhaps is what is the chances I'm going to churn, stop using Netflix over the next year. Later, they reported that a better machine learning problem to solve was to maximize the chance that I click on a movie and watch it to the end. And so that's what they use in their recommender system. But really, they have to constantly be looking at this balance between the problem that they really want to solve, I call that the metric, and the task that we solve in machine learning, which I call the loss. And this gap is prevalent, this mismatch between the two is prevalent in many problems. So for example, if you just take simple image problems, which we might solve classification tasks, detection tasks, or segmentation tasks, each of them has a standard loss function that we use in practice. For example, cross entropy for classification or L1 for detection. But there's a real evaluation metric that I care about, which is different, such as AUC for classification or intersection over union for segmentation. And the challenge is that these metrics I really care about are non-differentiable and hard to optimize, so we find these smooth approximations to give to a machine learning system. This gap can lead to a new kind of overfitting. So here I'm looking at a simple task, just classification on CFAR10, and if you look at the loss function on a validation set, it smoothly gets better with epochs, so with training. But if you look at the metric that you actually care about, which is AUC, it gets better, but at about 160 epochs, it starts getting worse again. So you see that the loss function of cross entropy is not a good approximation of AUC. And this loss metric gap is a very significant problem. There's many ways you can try to solve this. You can try to switch from, say, squared error to probability that you click and watch a movie to the end like Netflix did. Or you can come up with better, smooth approximations of metrics you care about, as been done in recent work. The challenge, though, is that the metrics that you care about are typically complex and multi-criteria, and they're really hard to approximate. And fundamentally, the product managers define those metrics, and the machine learning engineers optimize the loss function, and it's hard to figure out what a great way for these two teams to collaborate. To address this problem, with a team at Apple, we created a system we called adaptive loss alignment, where instead of using a loss function, we use a parameterized version of loss function, and we train for a few epochs our model, then we evaluate it on the metric that we actually care about, and then we use that to update the parameters of the loss function to bring it a little closer to the metric we care about. Here we use a reinforcement learning-based approach, where the reward function is the evaluation metric we care about, and the actions are these parameter optimizations. And at the crux of this is this parameterized version of the loss function, and here we borrow on existing work for parameterized losses, for example, in classification of curriculum learning, in metric learning, or in boosting, we just weighted data sets. This approach has led to a much better behavior. So if you go back to the simple CFAR 10 task, where we saw overfitting with the standard loss function, with adaptive loss alignment, we see that the AUC curve smoothly decreases over learning epochs. And perhaps most interestingly, surprisingly, the validation loss also gets better in this process. And this was not something that we designed for, so it's interesting to try to dig in and understand why that happens. And what we discovered is that the ALA automatically discovered the notion of curriculum learning. In particular, for this task, classification task, the type of parameterized loss function that we use said, how okay is it to confuse, let's say, a car with a truck, a ship, versus a dog and a cat? In the beginning, ALA says it's okay to confuse a car with a truck and ship, but not with a dog or a cat. And then over epochs, it starts narrowing down and says it's okay to confuse with a truck, and later on, it says the car can only be done independently. This notion, this heuristic, has been done in many papers with something called curriculum learning, but it's interesting to see that this approach to close the gap between loss functions and metrics using reinforcement learning automatically discovered that this heuristic was a really good idea. If you look at benchmark problems, we can achieve state-of-the-art performance on both image classification and metric learning using ALA. We've only recently published a paper on this approach, but we've been using it in production for quite a while, specifically for Face ID, for our on-device face recognition system. It has been indispensable to get the level of accuracy metrics that we needed for production deployment. In particular, with ALA, we've achieved about 10 to 20% false reject rate reduction for face matching, and a 10x reduction in false reject rate for attention detection in outdoor settings, which was one of the hardest tasks that we couldn't figure out another way to solve it. So it's really cool to see that aligning the metric and the loss function can have real impact in production systems. So this gap, this collaboration gap between machine learning engineers and product managers is just one of the gaps that we see in the real world across teams. We see many others. So for example, we see a gap between the quality assurance teams and machine learning engineers, or designers and machine learning engineers. And we need tools and techniques to help these teams collaborate better as we build intelligent applications. One of the cruxes in the collaboration gap between machine learning engineers, product owners, designers, and other stakeholders is how to make sure that everybody has the same degree of trust in the machine learning models that we build. So if you go back to the machine learning pipeline that we talked about earlier, the evaluation of those models is the crux of this collaboration between large sets of people across an organization. As a machine learning engineer, I typically just focus on optimizing a single function f, such as accuracy, and ignore everything else. And this can be really dangerous. To illustrate this, let's do a little user study. Thanks everybody for participating in the user study. So at the University of Washington, we have a serious problem. Our team mascot is a husky, and every time we have a game, we bring a husky to the stadium. The problem is that huskies can easily be confused with wolves. And if we bring a wolf to the stadium, thousands of people may die. You can laugh, but this is a serious issue. So at the University of Washington, we took the obvious approach for this. We trained the deep learning model to separate between wolves and huskies. So on our test set, the deep learning model got 95% accuracy. We have a meeting of the senior leadership at the University of Washington, and we decided that 95% accuracy was perfect for their problem. If in 1 in 20 games, there's a chance that thousands of people die, we're totally okay with that. So the question is, our model achieves the accuracy we wanted. It fits our requirements. Do you trust this model? Show of hands. Do you trust this model to solve this task? Do you not trust this model? If you don't trust this model, is it because you don't trust me? Thank you very much, David. Now, my student, Marco Ribeiro, came up with a system to better understand why a machine learning model makes a particular prediction. Because trusting a model is not just about an accuracy metric, but it's about having a deeper understanding of why a prediction is made. In fact, we want to have introspection to try to understand when a model works and when a model doesn't work. So in his system called LIME, one of the things it can do is find the parts of the input that were indispensable for making a decision. So for example, for this image on the left, where the model predicted a husky, on the right I'm showing the regions of the image were fundamental to the decision. Now I'm going to show you these areas for all the images. So pay close attention as the ones where we're predicting wolf. If you look closely, we don't have a wolf detector. We have a very, very deep snow detector. And if you dig even deeper, you realize that we had a fundamental problem with the data, that almost all of the images of wolves were taken in snowy settings, while most of the images of huskies were taken in non-snowy settings. So the model was picking up on something else that was in our data. So if Socrates, as reported by Plato, said, an unexamined life is not worth living, I would say that Marco would say, an unexamined model is not worth using. So what we're going to talk about is ways to better examine machine learning models. In 4 ways: interpretability, sufficiency, robustness, and consistency. To me, interpretability machine learning is about giving humans a mental model of how the machine is going to behave. One way to get a mental model is to use a very simple model like a simple decision tree or a sparse linear model. The problem is that these models are not very accurate. And if you start to make a decision tree more accurate, you end up with something very complicated, which is really hard to interpret. There's been a flurry of research in trying to find more flexible, interpretable classes of models, which is really good work. But the problem is that for real-world use cases, these models are not accurate enough. And in fact, the most accurate models, even the ones that are getting superhuman performance, are really hard to interpret. The goal of our work has been to increase the interpretability of the most accurate models out there. And we do this with an approach we call model agnostic. Instead of looking at the structure of the model, we consider a black box and try to interpret black box functions. And this allows us to interpret state-of-the-art models, allows us to interpret any existing models and future models haven't been invented yet, and compare different model classes in terms of their interpretations. The way we do that is by understanding that although the decision function might be really complex and hard to understand, if you zoom in locally, and maybe even more locally, it might look close to linear. So what we do is build a sparse linear approximation around each decision the model makes in a system we call LIME. So for a confusing image like this, if you give it to the inception neural network, it predicts it's an electric guitar. And if you look linearly, locally around this prediction, you'll see that the arm of the guitar that was the part that was most fundamental to this decision, the neck. If you look at the prediction of acoustic guitar, you see this more about the body, and it predicts it's a Labrador when it looks at the dog's head. Here's another example. If you're taking a machine learning class, maybe one that I taught, we often use a data set called the 20 news groups data set. This is a data set that's about 20 years old, and it had a bunch of postings from different news groups, which maybe today you call forums or Facebook pages or something like that. And they had topics, and the question is, based on the text of that news group, the text of that posting, can you decide which news group it belongs to? And the reason we use it in class is that basically any modern machine learning approach can get high accuracy. So even for the hardest task, like separating atheism from Christianity postings, any current modern approach gets something like 94% accuracy. But when Marco applied LIME to this task, he realized that the features he was using for predictions were things like the email address of the poster or the name. So this guy called Keith Jones that posts a lot and always in the atheism news group. So anything from Keith Jones is really easy to classify. To show this, Marco collected a recent data set of postings on atheism, Christianity, and using the model trained on the old data set, the accuracy went down to 57%. So this model did not generalize. And LIME was fundamental to discover this fundamental problem with the data. So we did a number of user studies to evaluate the system. One that we wanted to talk about today is, can folks without machine learning background use the explanations to fix problems in a model, kind of like what I described? So if you go back to the 20 news groups case, if you train on the old data and test on the recent data, then you get about 57% accuracy. So Marco wrote a bunch of regular expressions to clean the old data and trained on that, and now testing the recent data, he gets about 70% accuracy. And then we gave the model to Mechanical Turkers, the original one, and told them, cross out any words as part of explanations that you think should not have been used by the model in making a decision. And what we learned is with just 3 rounds of Mechanical Turk experiments, we're able to get better accuracy than Marco's hand-created regular expressions. So I fired him. Just joking, just joking. He's great. But it's amazing that folks without a machine learning background are able to discover issues with data and improve the performance of a model. If you go back to the user study that you did, to evaluate this, we wanted folks who could understand the notion of spurious correlations. So we took 27 graduate students who had taken at least 1 year of machine learning classes and asked them to go through this process. At first, we asked them if they trust a model, and about 60% of them trust the model, and about 40% had the snow insight, so identify this issue of spurious correlations. After seeing the explanations, 25 out of 27 no longer trusted the model, and 26 out of 27 had a snow insight. The real question here, though, is who is that one person who had this no insight and still trusted the model? But it's great. Using a system like this, you can discover issues with your data. Now, Lime was great at finding sparse explanations for a model, but there's also a notion of sufficiency conditions can find other types of explanations. So while Lime built a linear model around a prediction, with a system we call anchors, we find regions in the space where the model is stable, where predictions don't change. So, for example, if you take a standard task, which is given a set of demographic information of a person, can you predict if their salary is higher or lower than 50K? If you give this prediction to Lime, you get a pretty diffuse explanation that's hard to understand. But in this case, we discover a very simple anchor. For this model, if the education is high school or lower, then it predicts the salary is less than 50K with probability 95%. So this gives us a very good understanding of what this model is particularly doing. Let's look at a more challenging task. This task is called visual question answering. It's a pretty amazing task. For an image like this as an input, you can give it to a state-of-the-art model and say, what is the mustache made of? And the model says, banana. It's awesome. Or how many bananas are in the picture? And the model says 2, which is also super cool. But if you look at the anchors in this case, the stable parts of the question, you see the first one, the stable part is, the anchor is what? So any question of what gets the answer banana for this image. So what's the ground made of? Banana. What's the hair made of? Banana. What's the head of the United States? Banana. Oh, whoops, sorry. For the second question, the anchor is many, so any question with many gets the answer 2. Like, how many people are in the picture? 2. How many is too many? Obviously 2. So insights like this that anchors can give us a tremendous amount of understanding of how a model is behaving. We've done a number of user studies to evaluate it, but I can't cover those. But it led to more recent work that we've done on robustly understanding the behavior of machine learning models. Here, we're doing what we call adversarial debugging. The question here is, can you perturb an input and change the prediction of a model? There's been a lot of good work that, for example, says for a state-of-the-art model, we get an image like this where the model predicts panda. You add a small bit of perturbation that is imperceptible, and now the model predicts gibbon. This is good work, for example, if you try to break deep learning models for attacks. But it doesn't give me an intuitive understanding of when a model is working and not working and how to make it better. So we wanted a different approach to think about perturbations. We wanted to do what we call semantically meaningful perturbations. So let's look at 2 examples. For an image like this, I can ask a question like, what type of road sign is shown? And you'll say stop sign. That's super cool. Or for a paragraph like this, we can ask, how long is the Rhine? And it says 1,230 kilometers long, which is also really cool. However, if you change the first question from what type of road sign to which type of road sign, now it thinks it's a do not enter sign. And in the second question, if you add an extra question mark to the question, how long is the Rhine? Now it thinks it's 1,050,000 long. This is really problematic because the semantics are different, are the same, and humans can perceptibly see the change, but the answer changes very significantly. So our goal has been to find semantically equivalent adversarial examples for deep learning models, for machine learning models. So semantically equivalent here for us is using paraphrasing models, and adversarials means they change the prediction. So for example, for this image here, if you ask what color is the tray, it will say pink, which is super cool. But then we can find paraphrasings of this, and we discovered that if we change color to color for you, it now thinks it's green, so there's something against British English. And then we discover that it doesn't like foreigners like me that confuse what with which, so which color is the tray, now it's green. But more fundamentally, what we've discovered is that there's a lot of brittleness around these models where they overfit to the coverage of the data set. And we're simply highlighting limitations in the training data, and we can use that to improve our model. So in particular, we can come up with generalizations from this problem. So for example, changing what to which reduces accuracy by 4%, adding a question mark reduces accuracy by 3%. So we can automatically discover these kinds of general perturbations and use things as simple as data augmentation to improve the robustness of a model. So for example, we can discover perturbation rules for visual question answering tasks and sentiment analysis tasks, and without a drop in the accuracy or F1 scores, we can significantly reduce this kind of robustness issues. Machine learning models, especially highly flexible ones, are very prone to bugs like this. And we have to focus on semantically meaningful ways to understand it so that we can improve the performance of the systems. Let me give you another example of that. This is a notional consistency. So for an image like this, you can ask, how many jets are there in the image? And you'll say 6, which is pretty amazing. But then you ask, are there 6 jets in the image? And you'll say no. The problem is that the test set is not capturing this notion of inconsistency. First, it doesn't have coverage, although 13% of the answers had numbers in this data set, only 0.3% of the questions had numbers. So it's hard to cover everything, but in general, it's hard to have a data set that covers everything we can think about. And we have to discover other ways to evaluate these models. In this case, we took a very simple approach. We came up with some linguistic rules for transforming questions where we can discover problems like this. For example, changing the subject of a question into the answer of a question, or changing direct object, adjectival modifiers, and propositional phrases. These are all linguistic transformations that are well known that can be applied to augment a data set. And with this, with minimal impact on validation F1, we can significantly increase robustness of a system. In general, though, we have to increase the transparency and understanding around machine learning systems to build robust and honestly meaningful intelligent applications. The work that we've done on model agnostic explanations had a tremendous amount of impact in industry and research, with adoption throughout major companies, with systems in production from folks like Microsoft, through a large number of papers. It inspired DARPA's large-scale XAI program, and it has led to really cool new research. So for example, this is a paper that we're not part of, where they're using model-agnostic explanations to help prevent hypoxemia during surgery. So it's really cool to see the practical applications of this. And of course, it has led folks from Ernst Young to come up with the first solution to help gauge the trustworthiness of AI systems. Super cool. So today we talked about systems to help more people create, deploy, direct, and gain trust in machine learning applications. And these are really important topics. But it's also important to step back and realize that the decisions of AI are impacting people every day. And biases are prevalent in our society. Here are my kids watching a show that they love, which I hate. It's called Paw Patrol. In this show, there are 6 dogs that go in life-saving missions. There's only one girl dog, Sky. In almost every episode, she's tied to the sideline, dressed in pink, watching the other dogs overcome challenges. This is clearly not the example that I want to give my son or my daughter. And these biases are prevalent. And now that we're increasingly experiencing the world through devices and machine learning powered experiences, we have to be really careful not to perpetuate biases like this. There's been a tremendous amount of debate and exploration in the machine learning community in this area. And we're seeing real problems with real models. So here's an example, a sentiment analysis model that Google has in their Google Cloud service. If you take this input here, at Virgin American, hi, I did not get the points on my Evaluate account for my most recent flight to the United States. How do I add my flight and points to my account? If you give it to the Google Cloud natural language setting, it says this is a neutral sentence. Maybe it's a reasonable prediction. But here we're talking about the United States. If we change that country name from United States to Iran, now it's a negative sentence. And if we change to China, it's further negative sentence. I guess you get a lot more miles flying to China. So I'm more concerned. I don't know. If you look at state-of-the-art machine learning models like BERT, and you just look at the single word prediction, and here are models that were not trained on this, but the single word prediction for sentiment for the words United States or Australia, you get extremely positive sentiment. Now, if you look at all the countries in the world, just single word prediction, Turkey and Vietnam have completely negative sentiment, those words. That doesn't make sense. And in fact, if you look at the World Bank measurement of income across countries, you see that the model's prediction for the sentiment of a country name is directly correlated with the income of the country. This is a real problem. Isn't no problem. Take a state-of-the-art BERT question-answering model. Here's the input sentence. Nathan is a doctor. Nathan is not a doctor. Melissa is a doctor. Ask the question, who is a doctor? Model says, Nathan. Ask the question, Maria is not a nurse. Carlos is a nurse. Who is a nurse? Maria. More generally, person 1 is not an X, person 2 is an X. Take names according to census as male, female names, and if they're male, male, or female, female, the accuracy is almost the same. But if it's a female, male name, the accuracy drops tremendously for female names in the nurse setting and for male names in the doctor setting. This is a real problem. This is machine learning, state-of-the-art machine learning models that we often claim have superhuman performance, perpetuating biases in our society. Now, if you step back and look at systems that people work in production, systems that we build, like Face ID, or a system we built for incentivizing people to take healthier actions in their choices at Apple. When we're creating these technologies, we're working hard to create technologies for everyone. And we're actively thinking every day about how to mitigate biases like this in systems that we build. And there's been a tremendous amount of momentum in the machine learning community around theory and techniques for the ethics of AI. But the challenge, though, is that these methods often feel abstract and out of reach. When you're building an actual application, it's even hard to get started and know what you're going to do to address these fundamental challenges. So I believe that although we've fundamentally been working, and everything I've talked about today has been about machine learning systems that typically optimize business metrics, it's important to think about and build the next generation of systems that will directly help everyone address the ethical challenges of AI. Thank you.